All right, let's get right into it. Welcome to this explainer where we're going to dive into the incredibly precise, high-stakes surgical operation of blade dicing. If you've ever wondered exactly how those tiny, delicate semiconductor dies are separated from a massive silicon wafer without just shattering into a million pieces, well, you are definitely in the right place. Here is our roadmap for today. We'll start with the microchip separation challenge. Figure out how to master the process parameters, handle preparation and optical alignment, execute the perfect cut, run through the wash, dry, and cure phases, and wrap it all up with the final quality inspection. Let's go! Kicking things off with Section 1, the Microchip Separation Challenge. The ultimate goal here sounds pretty straightforward, right? We're taking a processed semiconductor wafer, one that's already been thinned down through backgrinding, and slicing it up into individual microchips. But doing this at a microscopic scale, that is a wildly perilous operation. I mean, we're not exactly sawing wood here. We are slicing through incredibly brittle silicon that is literally packed with nanometer-scale circuitry. To make sure that silicon actually survives the ordeal, we have to maintain absolute control over what we can call the three major enemies of dicing. Number 1 is mechanical stress. Apply too much force and the whole wafer just shatters. Number 2 is silicon chipping, which can happen on the top side where the circuits live, or on the back side. And number 3 is particulate contamination. Seriously, even a single microscopic speck of silicon dust can completely ruin a chip. Moving on to Section 2, mastering the process parameters. Before we make a single cut, we've got to set the extreme physical rules for this environment. Just look at this jaw-dropping number, 60,000. That is the maximum RPM of the spindle turning our cutting blade. It's a dizzying speed, but we absolutely need it. Why? Because a higher RPM actively reduces curve chipping, essentially giving us a much cleaner cut. But it's a massive tightrope walk. If you go that fast excessively, you're going to wear out your diamond blade in no time. Inside the machine, it's this intense balancing act. You've got your spindle speed pushing up to 60,000 RPM. Then there's the feed speed, how fast the wafer is actually moving through the blade, sitting between 10 and 80 millimeters per minute. Now, going faster means higher throughput, sure, but it aggressively ramps up mechanical stress. And finally, you've got coolant flow. You need about 1.5 to 3 liters per minute of deionized water to keep the blade cool, keep things lubricated, and relentlessly flush away that dangerous silicon debris. But here's the catch. That water introduces a whole new headache. High friction creates static, and static leads to ESD, or electrostatic discharge damage. A static shock will literally fry the microchip's sensitive circuit pads in an instant. So, to stop this during the sawing process, engineers do something brilliant. They bubble carbon dioxide directly into the deionized cooling water. This perfectly tunes the water's resistivity to exactly 1.0 to 2.0 megaohm centimeters, which neutralizes the electrical charge right on contact. It's just absolute genius. All right, now that we've got the physical parameters down, let's hit Section 3, preparation and optical alignment. Time to prep our silicon patient for surgery. This prep phase really boils down to two crucial steps. First, we carefully mount the incredibly thin wafer onto a protective tape frame. And second, we get it loaded into the machine for some highly advanced optical alignment. Let's look at that mounting first. The wafer gets mounted onto a specialized PVC or polyolefin tape that's stretched tightly across a rigid stainless steel or aluminum frame. And you have to roll this on with perfect uniform pressure, because honestly, a single trapped air bubble can spell total disaster. Now, for the really delicate dies, the ones thinner than 100 micrometers, they actually use a special UV curable tape. This stuff provides incredibly high adhesion during the violent sewing process, basically keeping those fragile chips locked perfectly in place. Next up is the setup. Once that framed wafer is secured onto a vacuum chuck table, the automated system takes the wheel. Automatic pattern recognition zeroes in on the wafer's microscopic scribe lines, those tiny empty streets running between the chips. It maps the exact X and Y coordinates to set the perfect cut pitch. On top of that, it runs a hairline check on the blade condition and strictly calibrates the blade's height against the chuck surface. Every single micro measurement here has to be flawless. Prep is done. The map is set, which brings us to Section 4, executing the perfect cut. It's time for the mechanical climax. Step 3 is the blade dicing itself. This is where the mechanical cuts are made along those X and Y scribe lines, using diamond-embedded resinoid or electroformed blades. And as that blade tears into the silicon, a continuous stream of that carbonated, CO2-injected DI water is blasted directly at the contact point. This dissipates the massive heat generated by the diamond blades and keeps that terrifying electrostatic discharge suppressed. Now, to solve that dreaded shipping problem we talked about earlier, engineers typically use two main approaches. You've got the single cut, which uses one spindle for a full depth pass. It's fast, but man, is it risky. Then you have the step cut, and this is where the magic really happens. It uses two separate blades in a sequence. First, a wider blade cuts 50 to 70% of the way down to prevent topside chipping. Right behind it, a narrower blade finishes the job to minimize backside chipping. It's beautifully designed to carve through that delicate silicon without shattering the edges. But here is the most anxiety-inducing part of the entire cut, what we can call the razor's edge. The blade can't just stop at the bottom of the silicon. To fully separate the dies, the blade has to cut exactly 20 to 40 micrometers deep into the mounting tape substrate right beneath it. If it doesn't go deep enough, the chips stay connected. But if it goes just a few micrometers too deep, it completely severs the tape and destroys the surgical table, holding the whole operation together. It is an astonishing level of Z-axis precision. Immediately after the trauma of the cut, we are moving to Section 5, wash, dry, and cure. So to stop the wet silicon slurry from drying like literal concrete onto the active circuit surfaces, the wafer is instantly transferred to a cleaning station, which is then followed by a highly specialized curing process for the tape. Let's talk about that tape curing first. Remember that ultra-sticky UV tape we used for the super thin dies? Well, now that the cutting is done, we actually need to get those chips off. By hitting the dicing tape with 365 nanometer wavelength ultraviolet light, the acrylic adhesive layer cross-links. This chemical reaction miraculously reduces the tape's adhesion strength by over 90%. Simultaneously, the cleaning process is wrapping up. The wafer gets blasted with high-pressure atomized water and air nozzles to strip away every single speck of dust. Then comes the high-speed spin dry. We're talking 2,000 to 3,000 RPM while blowing filtered nitrogen over the whole thing to guarantee a perfectly spot-free surface. So this intense nitrogen spin dry, combined with that massive 90% drop in stickiness from the UV light, means these tiny chips can eventually be picked up safely by needles without any microcracking. The surgery is complete, the patient is clean, and that brings us to Section 6, the final quality inspection. Step 6 is the post-saw inspection. And trust me, the margins for error here are basically non-existent. Automated optical inspection cameras, or sometimes technicians using manual high-magnification microscopes, meticulously scan the entire diced batch. They are looking for absolute perfection. That means zero residual kerf contamination and absolutely no misaligned cuts. The passing limits here are incredibly strict. Topside chipping cannot breach the active circuit area or guard ring. That usually means a hard limit of less than 15 micrometers. Backside chipping has a maximum depth limit of 25 micrometers, and there are absolutely zero die fly-offs allowed. Just to put that 15 micrometer topside limit into perspective for a second, that is a fraction of the width of a single human hair. If a chip breaks that limit, it's totally rejected, tossed out. Which brings us to the end of the process, leaving us with a truly mind-boggling thought. Knowing the violent speeds pushing 60,000 RPM, the extreme precision of 20 micrometer tape cuts, and the absolute zero-tolerance inspection limits required, how many perfectly diced, unchipped silicon dies are flawlessly powering the very device you're watching this explainer on right now? It really makes you appreciate the invisible, high-stakes engineering happening every single day to bring our modern technology to life. Thanks so much for joining me on this deep dive, and keep your curiosity sharp.